In the last video, I hinted that things were about to get wacky, and they are. So if we start where we left off in the last video, we started right over here looking at the distance to the nearest star. And just as a reminder, in this drawing right here, this depiction right here, this circle right here, this solar system circle, it's not the size of the sun. It's not the size of the orbits of the Earth or Pluto or the Kuiper belt. This is close to the size of the Oort cloud. And the actual orbit of Earth is about the diameter of the orbit of Earth is about 1/50,000th of this. So you wouldn't even see it on this. It would not even make up a pixel on this screen right here, much less the actual size of the sun or something much smaller. And just remember, that orbit of the Earth, that was at that huge distance. It takes 8 minutes to get for light to get from the sun to the Earth. This super long distance. If you shot a bullet at the sun from Earth, it would take you that 17 years to actually get to the sun. So once again, this huge distance wouldn't even show up on this picture. Now, what we saw in the last video is if you travel at unimaginably fast speeds, if you travel at 60,000 kilometers per hour. And I picked that speed because that's how fast Voyager 1 actually is traveling. That's one of the, I think, the fastest object we have out there in space right here. And it's actually kind of leaving the solar system as we speak. But even if you were able to get that fast, it would still take 80,000 years, 75 or 80,000 years to travel the 4.2 light years to the Alpha Centauri cluster of stars. To the nearest star, it would take 80,000 years. 80,000 years. And that scale of time is already an amount of time that I have trouble comprehending. As you can imagine, all of modern civilization has occurred definitely in the last 10,000 years, but most of recorded history is in the last 4,000 or 5,000 years. So this is 80,000 years to travel to the nearest star. So it's a huge distance. Another way to think about it is if the sun were the size of a basketball, and you put that basketball in London, if you wanted to do it in scale, the next closest star, which is actually a smaller basketball, right over here, Proxima Centauri, that smaller basketball, you would have to put in Kiev, Ukraine. Kiev, Ukraine, in order to have a similar scale. So these are basketballs sitting in these cities, and you would have to travel about 1,200 miles to place the next basketball. And these basketballs are representing these super huge things that we saw in the first video. The sun, if you actually made the Earth relative to these basketballs, these would be little grains of sand. So if there are any little small planets over here, they would have to be grains of sand in Kiev, Ukraine, versus the grain of sand in London. So this is a massive, massive distance. Already, at least in my mind, unimaginable. And when it gets really wacky is when you start realizing that even this is a super, super small distance relative to the galactic scale. So this whole depiction of kind of our neighborhood of stars, this thing over here is about, give or take, and we're doing rough estimates right here, it's about 30 light years. 30 light years. I'll just do LY for short. So that's about 30 light years. Now, and once again, you cannot actually, you can take pictures of our galaxy from our point of view, but you actually can't take a picture of the whole galaxy from above it. So these are going to be artist depictions. But if this is 30 light years, this drawing right here of kind of our local neighborhood of the galaxy, this right here is roughly, these are all approximations. This is about, let me do this in a darker color. This is about 1,000 light years. And this is the 1,000 light years of our sun's neighborhood, if you can even call it a neighborhood anymore. Even this isn't really a neighborhood if it takes you 80,000 years to get to your nearest neighbor. But this whole drawing over here, and it would take forever to get anywhere over here, it would be 1/30th of this. So it would be about that big. This whole drawing. And what's really going to blow your mind is this would be roughly a little bit more than a pixel on this drawing right here that spans 1,000 light years. But then when you start to really put it into perspective, so now let's zoom out a little bit. So this drawing right here, this 1,000 light years is now this 1,000 light years over here. So this is the local vicinity of the sun. And once again, the word local is used in a very liberal way at this point. So this right here is 1,000 light years. 1,000 light years. If you're sitting here, if you're sitting here and you're looking at an object that's sitting, let me do this in a darker color. If we're sitting here on Earth and we're looking at an object out here that's 500 light years away, we're looking at it as it was 500 years ago. Because the light that is reaching our eyeballs right now, or our telescopes right now, left this guy over here 500 years ago. Sorry, right, 500 years ago. In fact, he's not going to even be there anymore. He'll probably has moved around a little bit. So just even on this scale, we're already talking about these unimaginably huge distances. And then when we zoom out, this is kind of our local part of the galaxy right over here. This piece right here, this is called the Orion Spur. And people are still trying to work out exactly what the actual, the details of the actual shape of the Milky Way galaxy, the galaxy that we're in. But we're pretty sure, we're very sure we have these spiral arms and we have these spurs off of them. But it's actually very hard to come up with the actual shape, especially because you can't see a lot of the galaxy because it's kind of on the other side of the center. But really, just to get a sense of something that, at least, I mean, it blows my mind if you really think about what it's saying. These unbelievable distances show up as a little dot here. This whole drawing shows up as a dot here. Now, when we zoom out, over here, that dot would no longer even show up. It wouldn't even register a pixel on this drawing right over here. And then this whole drawing, this whole thing right over here, this whole picture is this grid, right over here. It is this right over here. So hopefully that gives you a sense of how small even our local neighborhood is relative to the galaxy as a whole. And the galaxy as a whole, just to give you a sense, has 200 to 400 billion stars. Billion stars, or maybe I should say solar systems, just to give you a sense that, when we saw the solar system, it's not just the sun. There's all this neat dynamic stuff in there, planets and asteroids and solar winds. And so there's 200 to 400 billion stars, and for the most part, 200 to 400 billion solar systems. So it's an unimaginably, I guess, a complex or huge place. And just to make it clear, even when we zoom in to this picture right here, and I think it was obvious based on telling you about this, that these little white pockets right here, this isn't one star, this isn't two stars, these are thousands of stars here. So when you go over here, each little blotch of white that you see, that's not a star, that's not 1,000 stars. We're starting to talk in the millions of stars when you look at certain blotches here and there. I mean, maybe it might be one star that's closer to you, or it might be a million stars that are far apart and that are just relatively close together, and everything has to be used in kind of loose terms here. And we'll talk more about other galaxies, but even this isn't the upper bound of galaxies. People believe the Andromeda galaxy has 1 trillion stars in it, 1 trillion solar systems. We're talking about these huge, immense distances. And so just to give you a sense of where we fit in the picture, this is a rough location of our sun. And remember, that little dot I drew just now is including millions of stars, millions of solar systems, already unimaginable distances. But if you really want to get the sense relative to the whole galaxy, this is an artist's depiction. Once again, we could never obviously get this perspective on the galaxy. It would take us forever to travel this far so that you could see the galaxy from above. But this is our best guess looking at things from our vantage point. We actually can't even see this whole area over here because it's on the other side of the center of the galaxy, which is super dense and super bright. And so it's very hard to see things on the other side. We think, or actually, there's a super massive black hole at the center of the galaxy, and we think that they're at the center of all or most galaxies. But the whole point of this video, actually this whole series of videos, this is just kind of, I don't know, put you in awe a little bit of just how huge this is. Because when you really think about the scales, it's I don't know, no words can really describe it. But just to give you a sense, we're about 25,000 light years. 25,000 light years from the center of the galaxy. So whenever even when we look at things in the center of the galaxy, that's as they were 25,000 years ago. It took 25,000 years for that light to get to us. I mean, when that light left the center of the galaxy, I won't even guess to think what humanity was like at that point in time. So it's these huge distances, and the whole galaxy over here. And once again, like solar systems, it's hard to say the edge of the galaxy, because there's always going to be a few more stars and other things orbiting around the galaxy as you go further and further out. But it gets less dense with stars. But the main density, the main disk, is about 100,000 light years. 100,000 light years is the diameter, roughly, of the main part of the galaxy, and it's about 1,000 light years thick. So you kind of imagine it as this disk, this thing that's fairly flat, but it's 1,000 light years thick. It's 1,000 light years thick. You would have to do this distance. You would have to do this distance 250 times just to go from the top part of the galaxy to the bottom part, much less going across the galaxy. So it might seem relatively flat, but it's still immensely, immensely thick. And just as another way to visualize it, if this thing right over here that includes the Oort cloud, roughly a light year in diameter, is a grain of sand, a millimeter in diameter grain of sand, then the universe as a whole is going to be the diameter of a football field. And if that, that might say, okay, well, those are two tractable things. I can imagine a grain of sand, a millimeter wide grain of sand in a football field. But remember that grain of sand is still 50 or 60,000 times the diameter of Earth's orbit. And Earth's orbit, it would still take a bullet or something traveling as fast as a jet plane 15 hours to just go half of that. Or sorry, not 15 years or 17 years. I forgot the exact number, but 15, 16, 17 years to even cover half of that distance. 30 years to cover an entire diameter of Earth. So 30 years just to cover the diameter of Earth's orbit. That's 1/60,000th of our little grain of sand in the football field. And just to kind of really, I don't know, have an appreciation for how amazing, I don't know, how mind-blowing this really is. This is actually a picture of the Milky Way galaxy, our galaxy, from our vantage point. As you can see, we're in the galaxy, so we're seeing, and this is looking towards the center. And even this picture, you start to appreciate the complexity of what 100 billion stars are. But what I really want to point out is even in this picture, when you're looking at these things, some of these things that look like stars, those aren't stars. Those are thousands of stars or millions of stars. Maybe it could be one star closer up, but when we're starting to approach the center of the galaxy, these are thousands and thousands and millions of stars or solar systems that we're actually looking at. So it really, it starts to boggle the mind to imagine what might actually be going on over there.